Hello, everyone. Today, we're going to be continuing with ThermoChem with a focus on state changes. And by state changes, I mean going from solid to liquid, liquid to gas, or the reverse. Okay, that's what I mean by state change. This is what today's focus is going to be on. So, we've so far discussed chemical reactions and energy release and absorption in those reactions. But chemical processes are not the only processes that require energy. Okay, state changes, melting, boiling, these are physical changes, but they still require energy. Okay, we've defined what it means when a process absorbs energy and when it releases it. When energy is being absorbed, it is endothermic, okay? And that is energy being put into the system, okay? And then would be a positive sign. It has an increase in energy, it's absorbing energy. When energy is released, then that system is losing energy. We call that exothermic, and is it a negative sign? Okay. So, for example, boiling, to boil water, you have to heat it up. So that would be an endothermic process because the water is absorbing that energy and becoming something with higher energy. Freezing would be an example of an exothermic. Okay, you're going from liquid water, it is releasing that energy and becoming something with less energy, which would be ice. Okay, so remember you have the endo and you have exo. So here you have a little quick diagram telling you that the higher you are, the more energy you have. Okay, and this is just a general diagram. So to go from solid to liquid, you have to melt it and look. Notice there's a small jump in energy, but from liquid to gas, that's where you usually have the bigger jump. Okay, and this is generally speaking. Generally speaking, gas has the highest energy. Well, gas will always have the highest energy, but the gaps will be different. Okay, so from solid to liquid, it's a little jump. From liquid to gas, it's a big jump. Okay, and we call going from solid to liquid, we call that melting. Liquid to gas is vaporization. You can also go from solid straight to a gas. That's called sublimation. Okay, and then when you want to go from gas to liquid, that's condensation. Liquid to solid is freezing. And you can also go from gas straight to solid, and that's deposition. Okay. So sublimation is from solid to gas, deposition is from gas to solid, the reverse. Everything has a forward and a reverse term. Okay. So we went through this. Endo is absorption, exo is release. Boiling, you're heating something up that is endothermic. Okay. And then these things would be the opposite. If you're condensing or depositing, you're going in the reverse. You're releasing energy. Okay, and then freezing would be exo, and then melting and sublimation. These things would be endo. Okay. So which of the following is or are exothermic? Boiling requires you to heat something up, so energy is being put in. So it's not boiling. Okay. Melting requires you to put energy in. Okay, you have to heat up something, heat up ice, heat up anything. You have to heat it up. So that is also not exo. Okay, freezing is the only one here that is exo. Okay. Okay. Now we're getting into the number aspects of things. Okay. So heat of fusion. Heat of fusion relates to solids and liquids. Okay, they call it heat of fusion because when you're going from liquid to solid, you are fusing, quote unquote, fusing things together. Okay, that's why they call it heat of fusion. So what this number here tells you is how much energy has to be released per mole of water in order for you to get your ice. Or you can think about it the reverse. You can think about it that this is how much energy you have to put in to ice in order to melt it to liquid water. Okay? So that's heat of fusion. And then heat of vaporization is a little more straightforward, vaporizing. Heat of vaporization is how much energy it takes to go from liquid to gas, or how much energy is being released when it goes from gas back to liquid. Okay? And notice the difference in the number. To go from solid to liquid, you only need to absorb this much. But to go from liquid to gas, you have to absorb more than what is it? That's almost it's like seven times more energy. Okay, almost 7 times more energy. Okay, that's why this gap is like this. you have this little jump to go from solid to liquid, but liquid to gas, the jump is a lot bigger. You need a lot more energy to go from liquid to gas than you do from solid to liquid. And that's what these numbers here tell you. Okay, that's what the heat of fusion, heat of vaporization tell you. Okay. So again, release is exo, absorption is endo. Okay. If we're talking about exo for this number, heat of fusion, then you're going from liquid to solid. If we're talking about exo for vaporization, you're going from gas to liquid. If it's endo and they're absorbing, it's the opposite. Okay. And this little graph is giving you the same idea. So remember I said, generally speaking, liquid to gas is going to be higher. The blue bars are your heat of fusion. So that's solid to liquid or liquid to solid. And the teal or the lighter, well, no, it's more of a, you can see the color difference. I'm not sure exactly what color that is, but it's higher than the heat of fusion. And that is the case for most chemicals, okay? You have butane here, which is commonly used for lighters. You have diethyl ether, you have water, you have mercury. All of them have higher heats of vaporization than they do fusion, okay? So generally speaking, just know going from liquid to gas is always going to be harder than going from solid to liquid, okay? This goes into energy calculations. I don't want to focus on this stuff just yet. This is saying, so the heat of vaporization for butane is 24 kilojoules per mole. How much energy will be required to vaporize 2 moles? Multiply that number by 2, you get your 48. Hey, but I don't want to get into any calculations just yet. I want to get into the graphical portion. Here we go. Okay, the numbers, we'll worry about the numbers later. So now, when you have these heats of vaporization and your heats of fusion, you can put them together to make something called a heating curve, okay? What a heating curve tells you is you can look at it for any substance. Every substance has a different heating curve. But what you can look at it and see, okay, when do things melt, when do things vaporize, and so on and so forth. You have to make the assumption that the bottom of the graph is always solid, okay? The bottom of the graph is always solid. So it cuts up into 2 portions, okay? So where you see it flatlining is where you see the separation, okay? This is what I mean. So everything, if we're down here, we're in solid. If we're down here, we're solid. If we're in the middle, we're liquid. And if we're above this one, we're in gas form, okay? Okay. Where do these flat lines come from? So remember, everything has a heat of fusion and everything has a heat of vaporization, right? There's a certain number associated with it. Where you see the flat line is where a transition happens. So this is for water specifically. We know that water freezes at 0 degrees Celsius. If water freezes at 0 degrees Celsius, that also means it melts at 0 degrees Celsius, okay? So when we're below 0 degrees, anything below 0 degrees, we know it's ice. But once you get to zero, you can't go up anymore because we're still ice. Before we can increase temperature, we have to transition to liquid. That's what this flat line is here, okay? We go from a certain temperature, -25, we end up at 0. Now we're melting. Melting requires energy. This is the heat of fusion, okay? Melting requires energy. So this piece right here, this is your fusion, okay? This is your heat of fusion. I want you to take note of the length of the flat line, okay? Because in this graph, there are 2 flat lines. There's one flat line here, and there's another flat line here. Which one is longer? The one up top. The reason the one up top is longer is because this is your heat of vaporization. As we saw earlier, heat of vaporization is larger than heat of fusion. What that means is that going from liquid to gas takes more energy. And if it takes more energy, then it's obviously going to take longer, okay? So that's why the bar up top is longer than the bar down here, because melting is a lot faster than boiling or vaporizing, okay? So just this is how you would read this graph. So where anything below 0 degrees, you're ice. Okay, you get to 0, now the ice has to melt. It's melting. Once you get to this point where it starts going up again, now we're liquid. This diagonal bar, this whole thing is liquid. We heat up, it heats up, it heats up. Then we get to 100 degrees Celsius. Now we're boiling, okay? But the water has to heat up first. It's heating up, and then once you get to point E, this is where you start to boil, okay? So if you want to know all these terms, okay, B is where you first get to the melting point. At C, it's all liquid. At D, it's start now you're at boiling, and now at E, it's all gas, and then it just continues to heat up from there. Okay, that's how you note those different points. Please stop with the emails. That is how you read a heating curve. Let's see if we can get a question associated with this. Okay. I just want you guys to be able to read heating curves. Here they're pointing out everything we just discussed. Okay. In the last assignment, I made a note about a term. Okay, that term is called heat capacity. What heat capacity is how much energy you need to heat something up. That's the basic gist of it. So the higher the specific heat, the more energy you need to heat something up at the same rate, okay? So for example, let's say we have copper metal and we have liquid water. Liquid water has a higher heat capacity than the copper. What that means is that if you put a pot of water on the stove and heated it up, it would heat up slower than if you took some copper wiring and stuck it in the fire. The copper would heat up faster because it has a lower specific heat. Okay, that means it needs less energy to get hot. Okay, that's all that number means. So when you see a graph like this with different lines, with different slopes, the one at the bottom, D, has the highest. This has the highest heat capacity. You can tell that because it's heating up the slowest with the same amount of energy. Every single one of these substances is getting given the same amount of energy, but D is increasing the slowest. That means it has the highest heat capacity. Okay, so this question, which substance has the lowest heat capacity, you have to look at which one is heating up the fastest. A is heating up the fastest, so that would be the one with the lowest heat capacity. So that's what that term means, okay? That's what that term means, okay? I believe that's the gist of this section. I don't want to go too crazy, okay? What I wanted you to get out of today is how to read a heating curve, okay? You have heat of fusion, you have heat of vaporization, okay? And they have values. It's how much energy you need in order to get from one state to the next, okay? But depending on the substance, you can have different heats of fusion and different heats of vaporization. Let's look at this case, for example. I don't know what chemical this is. I'm not worried about the question, so ignore the question. I don't know what chemical this is. Well, they actually did tell you, sodium chloride. So this is salt, okay? This is salt. It's in the title. Look at the length of the flat lines. Again, look at the length of the flat lines. This flat line is shorter than the one on the bottom now. What that means is melting salt, this is sodium chloride, melting salt takes more energy than it does to vaporize it. Okay, that's what that means. Okay, but so that's what these bars tell you. So there's two things you want to look at. Okay, the flat lines will tell you right away if it's harder to vaporize it or if it's harder to melt it. That's all you can get from the graph, okay, in terms of the flat lines. And then where you see the straight lines at, that tells you the boiling points and the melting points. So here, I know that the freezing point for water is 0, and it boils at 100. Okay, I get that straight from the graph. Okay, that's the important information you can get from a heating curve. Okay, and I believe that's everything for this section. Okay, before you start getting into calculations, I don't want to get too crazy. Okay, because then this thing starts to get super long. Okay, so that's it for today. I'm about to go over the work and give over some more examples, and then we will call it one moment. Okay, so for today, you have a heating curve worksheet. Okay, there are no major calculations. I didn't want to do any calculations, anything too crazy yet. I just wanted you guys to see how you would read a heating curve. Okay, so the flat lines give you information and the slopes give you information. Okay, so for example, again, you have to make the assumption that it's always split into solid, liquid, and gas. It's in phases. The bottom of the graph, where you start at 0, you always assume that that is solid. Okay. So number 1 here tells you what is the boiling point of this substance. Okay. That's going to be at one of the flat lines. Okay. It's going to be at one of the flat lines. It's either going to be the first one or it's going to be the second one. Okay. Since you're starting at solid on the bottom, boiling is what? Boiling is liquid to gas. Okay. Boiling is liquid to gas. Okay. And if it's going from liquid to gas, which flat line should we be looking at? Okay. At the bottom, you're solid. This first flat line is the first transition. So this is solid to liquid. This right here is solid to liquid. So it's not the bottom one. It's going to be the top one in this case. So then where does the flat line meet the Y graph or the Y bar? Okay. Where's the intersection? And that will be your answer for number 1. And same thing with number 2. Okay. Number 3, does this substance have a greater heat of fusion or a greater heat of vaporization? Okay, that's what we were talking about here. Which one has the longer line? Which flat line is longer? The bottom one or the top one? Okay, that's how you answer that question. And you have to know vaporization is from liquid to gas, fusion is from solid to liquid. So depending on which flat line is longer, that'll tell you that answer. Okay, that's how you do number 3. Number 4 and 5, you just have to look at the graph and get that information. 6 is the only one that may be a little different. 6 is the only one that requires a calculation. Okay, it's saying which will have a greater specific heat. Okay, specific heat capacity. So this is heat capacity. Okay, specific heat is a shorter way of saying it, but this is the same thing as there's capacity. Okay, this is specific heat capacity. Well, let me not. I can't cover the question, so let me not do that. Okay, so which will have a greater specific heat capacity, the solid form or the liquid form? What they're asking you is that is it easier to heat up the let's say this isn't water, but let's pretend it's water. Is it easier to heat up ice or is it easier to heat up the liquid water? Which one is it easier to heat up? Depending on what form you're in, it can change. Okay. You might think because it's water that it's the same no matter what, but that's not true. Okay. So how you answer this question is you need to look at your answers for 4 and 5, actually. So how long it takes is how you do that calculation. So what you do is you take the time and you divide the temperature change by it. Okay. So it is your change in temperature over your change in time. Okay. Lowercase t is time, capital T is temperature. Okay. So from solid to liquid, it went from 0 degrees to 20 degrees. Okay. It went from 0 degrees to 20 degrees. How long did that take? It took 1 minute. Okay. It took 1 minute. So then that's 20 degrees per minute. That's 20 degrees Celsius per minute. Okay. So that's your value for that. Now you have to check the liquid one and see whichever one is higher. Whichever one is higher, that's how you figure out the answer to that question. And then number 7, ask you to draw your own heating curve. giving you the following information. They tell you where the melting point is. They tell you what the boiling point is. K is in Kelvin. That's just the unit. Okay, you don't have to worry about that when you're drawing. And you don't have to give me a fancy schmancy graph. Okay, you can just do something really quickly. All I'm looking for is where the straight lines are and where the flat lines are. Okay, so it's just going to look something like boom, and then it's going to flatline, then it's going to go up again, then it's going to flatline. This is all I'm looking for. The important parts are going to be where the flat lines happen. So then you have to label these the right numbers. That's it. But it doesn't have to be a fancy schmancy graph. It can be hand drawn. You can do it on the computer if you want. Okay, but it doesn't have to be fancy schmancy. All you need for that graph is to put the flat lines in the right spot. Okay. So they tell you where the melting point is. That's where the first flat line is going to be. They tell you where the boiling point is. That's where the second flat line is going to be. And then how long you make the flat lines relative to each other is based on this. Okay. Okay. It says the specific heat of the liquid is greater than the specific heat of the solid. What that means is that it takes more energy to heat up the liquid than it does to heat up the solid. And that'll tell you how long you should make the lines in terms of the flat and the slope, okay? Or how fast it increases. That's all that is, okay? That's what that part is telling you, okay? So that's it for today. That's heating curves. That's how you read heating curves. I didn't want to get too deep into calculations, especially with us getting close to wrapping things up at the end of the year, okay? That's it for today. If you have any questions, as always, you can reach out. Happy Tuesday. Hope you guys had a good Memorial Day weekend. Happy Tuesday. Enjoy the rest of it. Be safe. Have a good one.